Don't be afraid.
We are live now, so welcome everybody. Welcome to the Law Physics webinars. Today is a special day because we are gonna do the dark matter day. So it's gonna be a whole Law Physics episode only dedicated to dark matter, and especially dark matter, and also about Latin America. So today we're gonna have a very interesting program because we have physicists and astrophysicists working in different areas across Latin America that in somehow they are related with dark matter. That is going to be our main thread during all this emission. So we're going to have, for instance, starting the series is going to be Farinaldo Queiroz from Brazil, then Andreas Reisnegger from the Universidad Católica de Chile, José Basso from Universidad Católica del Perú, Sergei Kovalenko from Universidad Técnica Federico Santa Maria, Rogério Rosenfeld from UNESP in Brazil, and Juan Carlos Muñoz from Universidad de Antioquia in Colombia. So this is going to be a very nice. It's the first time that we're trying this connection because we're gonna be in direct connection. Sorry, with three universities: Universidad de Antioquia in Medellín. They are now broadcasting this transmission in the Aula 03. Museo Universitario Bloque 15, Universidad de Antioquia. Also in Lima, in Peru, in the Pontificia Universidad Católica del Perú, in which this is the transmission in the Aulario A409. And in Santiago de Chile, in the Pontificia Universidad Católica de Chile, and in the Auditorio Ninoslav Branic. So today we are going to have this presentation, and we can already go to the topics to each of the presentations. So one reminder to the people that is following this transmission that you are watching this via YouTube, all the questions that you have, you can start to type it in the chat. YouTube has a chat in which you can write all this stuff. And then after each presentation, we are going to have some few minutes for some interesting questions that can help us to develop all these this quest for the dark matter. So if Farinaldo wants to start, that we have here is the first speaker. Hi, Farinaldo.
Hey.
Hi. So whenever you want, you can start.
All right.
Yeah.
So I'm gonna share the slides. Can you all see the slide?
No, now we can see you.
Okay. Yes.
You have to make share screen.
Mm-hmm. Yeah.
Yeah, if you can make full screen, yeah.
All right. Okay. Yeah. Working.
Yeah.
Okay. So, first, thank all the organizers for this opportunity. I'm quite proud for being a Latino American physicist working on dark matter in this epic moment, I would say. So, having an event on dark matter by Latin Americans is something beyond average, I would say. So this talk, as emphasized on the webpage, is targeted for bachelor students. So be not very deep into the subject, but I believe that every one of you will be able to understand what I'm trying to do. So first, always I start my talks addressing my take-home messages, which are very, very, very simple, super simple. So first, the one is sort of an advertisement, which is why I believe this is the right moment to become an astroparticle physicist. And the second is that I think you will all see and agree with me that dark matter research is a multidisciplinary endeavor. And I must warn you, it's very addictive because I take a dark matter pill every single day, I should say. So I would like first to start discussing what are the evidences for dark matter. And one of the evidences for dark matter, which was the very first one, and I think all students are fascinated by the early universe cosmology, physics of the universe, fundamental laws of nature. So that's one of the first things that comes into textbooks. So dark matter is key to the evolution of the universe Why is that? So for those who haven't seen an extended course on cosmology, you should be aware of that the temperature of the universe, or the temperature of the photons in our universe are proportional to the size of, inversely proportional to the size of the universe. So the bigger the universe, the smaller the temperature. That means that in the early universe, when the size was very, very small, we had very, very high temperatures. In other words, what I'm trying to say is early universe means hot universe. So why am I saying this? Because of the following sentence. In the early universe, the universe was hot, and the matter, the constituents of the early universe were tightly coupled to each other. So they were very tightly coupled. And you needed something, we need something that has to decouple from that early enough and start forming clumps of matter through gravity, and then evolve with time and form the galaxies we observe today. So we need is not Farinaldo saying, and it's not Roberto saying, or Diego saying. Is we need, the data tells us that we need something that has to decouple early enough and through gravity form the galaxies and the structures we observe today. And what that is? Dark matter. So that's one of the most important and compelling evidences for dark matter, which is the presence of dark matter in the evolution of our universe. So as you see, so people have assessed and tested these hypotheses by using doing cosmological simulations. What these are simply is that you pick lots of particles and put in a huge volume and let them evolve through gravity. As you've seen, for those who are in the second year bachelor degree, you've seen already that the gravitational force from Newton. So mass attracts mass, right? And is inversely proportional to r squared. And what it means, what I'm trying to say is, whenever you have mass, whenever you have a mass, these will attract each other, and they will form clumps and clumps of matter and evolve with time. And this is what this is just an ensemble of particles which you have in a large volume and let them evolve through the Newton's law, basically. And what you get are those filaments of matter at very, very large scales, and these very, very bright points right here or here or there throughout this picture are simply galaxies and clusters of galaxies. And the nice thing about this picture, beyond everything I've just said, is that at very large scales, these cosmological simulations agree with the observations. So if you have the universe is comprised of dark matter. Dark matter is sufficient to explain the formation of galaxies and clusters of galaxies. Okay? So that's very, very, very important. One second evidence for dark matter, again, for those who have seen, or at least in the second year of bachelor degree, is that this is like these now YouTube videos that people are posting every single day. 3 steps to the dark matter discovery. So in these 3 steps to this dark matter discovery, it goes as follows. So imagine you're here, you're a galaxy of mass M, capital M, and then surrounding their galaxy, you have a star of mass small m. And the distance between the center of this galaxy of capital M and the star of mass m are r, is r. And if this forms is a stable system, it means that the gravitational force is just balanced by the centrifugal force. And what it means is you just solve this equation, which is the step 2, centrifugal force equal to the gravitational force. When you solve this, if m, capital M, is constant, does not depend on the distance, what I'm trying to say, there are no more mass beyond this radius r. Therefore, if you assume that, and that is true, then V, the velocity of that star moving around their galaxy, should be proportional to 1 over square root of R. So that's what you get just from basic physics. However, what you observe is something entirely different. What you observe is these data points here in this figure below. This curve here just fits the data points, which you see is not at all, nothing close from 1 over square root of R, which is this plot here, yellow in the bottom. So you should expect something like this, and you observe something like this. So what I'm trying to say is you need either two things. One, my reasoning, the laws I'm applying are wrong, are not valid at this scale. Or two, this mass does depend on R. So throughout this talk, I'll be focused on the latter. So if that mass depends on R, it means that in this galaxy, in this step 1 case I was just mentioning, this mass encompasses, surrounds far beyond this distance R. So you have actually a halo of mass around that star. So what we call it is a dark matter halo. Why dark? Because we don't see it. We don't see the visible light coming from that mass beyond R. We don't see it. So therefore, we call it dark. This is one of the major evidence for dark matter, and is one of the proofs that we have a dark matter halo in galaxies. Not all galaxies, but some galaxies. So based on that, we have a variety of experiments today searching for dark matter. Okay. So the third one, for the students in the audience who haven't played with this, I strongly advise you to it. So you just link this link here in red. So you access the WMAP. It's not actually Planck, it's the WMAP website, where what you can do is the following. You can play and find out how much dark matter you need in your universe. You can play what kind of universe do you want. You want the universe with dark matter, without dark matter, and with whatever you want, okay? So just look at these two pictures. So these two pictures are the following. Look how amazing this is. I get goosebumps just talking about this. So looking at the photons, look at this, looking at the photons that come from distant different points in our universe, the difference in temperature of these photons are tied to the universe observables, such as the abundance of dark matter in our universe. Therefore, you can use this tool from WMAP and play with it. So what you do is, let's assume that I don't want dark matter, I don't like dark matter, Farinaldi is just a crazy guy. So let's see what he's saying is really true. So these black points here in this curve are the data points. So this is data, you cannot mess up with it. Okay, so the data points, I want to fit this curve. And then I'm going to assume that the universe does not have dark matter at all. So what you get from the predictions is that you get this green curve. So you don't fit the data whatsoever. In order to fit the data, you need the universe to be comprised of 27% of dark matter. It's not 20 and it's not 40. Why emphasize this? Because it's a precise assessment of dark matter abundance in our universe. Using data is not someone's opinions or taste, it's data. Data tell us that the universe needs dark matter, and that abundance has to be 27%. Okay, so in overall, we have a need for dark matter from across different time scales of the universe evolution and different distance scales of the universe today. And that said, what can we learn from this from a particle physics point of view? So I just remind you that everything around us are ruled by fundamental laws of nature, right? And the same way these laws of nature are described in terms of elementary particles. Therefore, it's quite plausible and natural that to assume that this dark matter is also described by elementary particles. And what not just me, but many physicists throughout the world have assumed so far, and start trying to search for signals of those dark matter particles. As you can see in this plot, this slide, this is how many experiments, just is a piece, okay? They're not all of them, just some of them. How many experiments from collider, direct detection, which I'm gonna explain later, that somehow are sensitive to dark matter signals or are devoted partially to search for dark matter. There are many of them. The ones in boldface are the ones which we have Latin American members involved in, such as CMS, Altas Bavaria. I won't go through all of them. There are so many. So just to give you a snapshot of how much dark matter is important. Some of these collaborations, there are 2,000–3,000 people involved. So it's not just crazy guy on the other side of the screen who is trying to convey and explain to you, advocate for the presence of dark matter in your universe. There are thousands of not just crazy, but amazing physicists trying to search for signs of these little things, okay? And hopefully in the future, we'll be talking about this dark Latin America experiment. So, so how do we search for these dark matter particles? There are three of them. I'll mention the first one. The first one is called collider. So what you do with collider is just take the LHC, which is the largest hadron collider ever built in mankind, and what you do is you crash proton beams together, and by crashing these beams together at very high energies, you probe the fundamental laws of nature. And by probing the fundamental laws of nature, you also might produce dark matter particles. And LHC has been intensely searching for signs of these dark matter particles. And you can see in the picture, Diego is already with a microphone ready to give some good news as soon as we have them. Okay. Another way of searching for dark matter is through direct detection. What does direct detection stands for? Direct detection stands for you have a dark matter particle in red here, and just scatters off nucleus and deposits some energy. And depending on how this energy was deposited in a given target, you can discriminate signal from background, and by doing so, you can find signals of dark matter. And there are many Latin American researchers involved in these searches. And the third one, and just before I go to the third one, is just to give an idea. On this top one was just a guy who made a cave. Out of a cave, he made a hotel. And some physicists, out of a cave, they do direct detection experiments. Okay, and this little thing might just unveil one of the most exciting, puzzling, open questions in nature. The last one is called indirect detection. What indirect detection means? If you have remember, we've seen before that dark matter is in galaxies, and there is a dark matter halo in galaxies. And in this dark matter halo, okay, if these dark matter particles, they are concentrated in regions where the dark matter density is expected to be very, very high. These dark matter particles just might find itself. One dark matter particle might find its anti-partner or not, and they might just annihilate like matter antimatter. Similar, it's not quite the same, but it's similar to matter antimatter when they annihilate. We've seen even in Star Wars movies. So matter antimatter. So two particles, when they might find each other, they might self-annihilate and produce all kind of signals, okay? From gamma rays to neutrinos and antimatter. There are many others. And you can use and search for those byproducts of dark matter annihilation, gamma rays, neutrinos, antimatter, using ground-based telescopes such as HASS and CTA in the bottom. HASS and CTA are this right one, the bottom. Fermilab is the satellite, this on the left. And you can also search for neutrinos with underground detectors such as IceCube, and also another satellite such as AMS, which is search for antimatter. So we go from satellite to underground and ground-based detectors trying to search for signals of dark matter. Okay, so look, just to conclude, I've talked about pretty cool physics. I've talked about early universe, galaxy formation, laws of nature, and you can search for gamma rays, neutrinos, antimatter. And there are even models involved, okay, particle physics models involved. There are so many physics involved, which is just fascinating and addictive. The reason why I conclude this, why is the right moment to become an astroparticle physicist? Because there's so much physics involved and there's so much data involved. Every single year we have new data and new excitement. I mean, it's so passionate. I'm passionate about what I do, and I think if you engage on this topic, you will too. Thank you.
Thank you very much, Farinaldo. So I guess we can have some questions if there are people that want to address to Farinaldo. I don't know. I'm just gonna, okay, stop to present this. Okay. Okay, I don't know if there are some very short questions from the, I'm gonna take just in YouTube. So for the moment, no, and I guess one of the best stuff that Farinaldo was saying is that here we are trying to provide like a sample of physicists and astrophysicists working in line that are related with their matter. But Farinaldo was right. They said that there are a lot of Latin American physicists around the world, not just only in Latin America, that is participating in this collaboration. Those they are making a very big impact in the field. So if for the moment I don't see any question, remember that you can make all the questions via YouTube if you are in one of these, you are not in the rooms in which we are broadcasting this. Otherwise, at the end, we're going to have the roundtable and we're going to be able to talk with more relaxed about all what we have seen during the day. So maybe we can pass now to the next speaker. That is going to be Andrea Reisneger from Pontificia Universidad Católica de Chile, and he will talk about the Cherenkov telescope array. So, Andrea, you can start.
Hi, can you hear us?
Yes, I can hear you.
Okay, good.
And what about the...
Well, we will put the presentation.
Yeah.
And just 1 second.
I can see the auditorium from the Catholic University.
Yeah, it's almost full.
Yeah. That's good.
Okay. Okay, we should be in full screen now, right?
Yes, we can see it perfectly.
Okay.
So whenever you want to start, Andreas.
Okay. Thank you very much, Roberto and Germán and everyone else for organizing this and for inviting me to speak about the Cherenkov telescope array, which is a very exciting observatory that will be here in Chile in the next few years. As was announced, I'm here at the Catholic University in Santiago, and I'm a Chilean representative in the CTA Consortium Board. And well, a broad outline of what CTA is. CTA is an international project to build by far the largest gamma ray observatory in the world. And this will consist of 2 observatories actually, one in the south, which means in the Atacama Desert at the Paranal site in northern Chile, which will be about 100 telescopes, and another northern array of about 20 telescopes on the Canary Islands, La Palma and Spain. The CTA Science Consortium, which has been working on the science case for this and the key science projects to be carried out, consists now of 32 different countries with more than 1,000 scientists, and at least 3 Latin American countries are in the consortium, which are Brazil, which is very active, Argentina, and Chile. The center of mass of the CTA Science Consortium is in Europe. Now the main offices are in Bologna, which is the central administration of CTA, and Zeuthen in Germany, where the data and computing center is. And CTA will cover energies from about 20 GeV to 300 TeV. So that's the highest photon energies that we can observe. And this, of course, as Farinaldo pointed out, this is interesting for astrophysics, for fundamental physics, and for their intersection, which we call astroparticle physics. And well, so if we look at the electromagnetic spectrum, we have at the lowest energies, or longest wavelengths, we have the radio waves, and well, we have the whole spectrum that we know. And we have many orders of magnitude at the opposite end of the highest energies and the smallest wavelengths, which are the gamma rays. And on the upper end of the gamma rays is where CTA will operate. So that is, of course, the most interesting range for particle physics and for the most energetic processes in the universe. So among these processes, we have gamma ray bursts, we have supernova remnants, active galactic nuclei, and pulsars. All of these phenomena accelerate particles. They accelerate charged particles to very high energies, and these charged particles then radiate gamma rays. And well, at the moment, the gamma ray observatories operating in the higher energies are, on the one hand, Fermi, which operates in space, so it has very little background, but it has a small collecting area, so it can observe mostly the gamma rays at not so high energies, basically around GeV. And then there are the ground-based telescopes, Veritas, MAGIC, and HESS, in North America, in the Canary Islands, and in Namibia, which are observing the highest energy gamma rays. And these are observatories which have somewhere between 2 and 5 telescopes, which are the state of the art at this moment. Now, these ground-based telescopes and the future Cherenkov telescope array operate by the Cherenkov technique, which is basically that we have a very high energy gamma ray coming in from space into the Earth's atmosphere, and there it interacts with the particles in the atmosphere, generates a shower of charged particles which move at velocities which are higher than the speed of light in the medium in the atmosphere, and therefore they generate Cherenkov radiation in the direction in which they are moving. And this Cherenkov radiation is optical light which can be detected by ground-based telescopes. So these telescopes generate images like the one we see here. And if we have several of those telescopes, we will get several images and we can basically triangulate where the gamma ray came from. And from the size of these signals, we can get the energy of the gamma ray, and from the shape, we can distinguish what's a gamma ray compared to, for example, cosmic rays, which are charged particles of high energy and which generate a somewhat different signature, a different image. So the idea with CTA is to have these ground-based optical telescopes to detect the gamma rays, but many more than in the current observatories. So there will be telescopes of 3 different sizes. On the southern side, there will be telescopes of all 3 sizes. In the northern telescope, in the northern side, there will be only the large and the medium-sized telescopes, which of course will have a performance which is much better than the current observatories. So here are the 2 sites where they are located in the Canary Islands and in the Atacama Desert in Chile. And here's a comparison of the sensitivity of CTA compared to the current observatories. Here we have MAGIC, HESS, Veritas, and we see that CTA has a similar energy coverage, but about an order of magnitude better sensitivity. And in addition, and not shown here, it will also have a much better angular resolution. So it will produce better images than the present day observatories. The key science drivers for CTA are to understand the origin of cosmic rays and their role in the universe. So basically this process of accelerating particles in very violent processes in the universe. And these charged particles then produce the gamma rays. And the advantage of the gamma rays over the charged particles is that the charged particles will be affected by interstellar or intergalactic magnetic fields, and therefore don't travel along straight lines, so we don't really know where they come from. Whereas the gamma rays do travel on straight lines, and therefore we can produce images of the sources. And we can study particle acceleration around black holes, which is in a sense a particular case of the above. But then there are the ways of studying the nature of matter, in particular dark matter, and physics beyond the standard model. For example, the possibility of Lorentz invariance violation. So this experiment or observatory will be of interest to astronomers and particle physicists. On the other hand, it will be very important to observe the same sources in other wavelengths, which particularly here in Chile we are very well equipped to do so, because we have many other observatories operating here in Chile between the optical and the radio range. The main target for CTA South is the galactic center, which is also a particularly important subject of study here at the Catholic University. The galactic center is the strongest concentration of dark matter in our cosmic neighborhood. So it will be the source from which we would expect the strongest signal from, for example, the annihilation of dark matter particles, which would produce or could produce high energy gamma rays. But on the other hand, in the galactic center region, there are many other sources of very high energy gamma rays, such as supernova remnants, pulsars, cosmic rays as accelerated by different sources which hit molecular clouds and generate gamma rays, and a possible tevatron that's an accelerator of charged particles with PeV, 10 to the 15 electron volt energies, which is suspected to exist near the galactic center. So here you see images of the galactic center regions produced by Fermi and by Hess on different scales, and of course in different energy ranges. And you see that there is always a strong emission from the galactic center, which will be much better studied by CTA. Of course, since there are so many sources together, it will be important to have good models to disentangle all these signals. So here's a timeline for CTA. You see in the next few years, CTA will be built up progressively, and it should start actual science operations sometime around 2022 or so. Well, CTA will function as an observatory to which astronomers or physicists can make observing proposals and get time to observe their favorite sources. However, there are also key science programs which are designed by the CTA consortium. And during the first years, the key science programs will take up most of the observing time. The open time will be a smaller amount at the beginning. So it is particularly important for us here in Chile that we will have 10% of the observing time throughout. So at the beginning, we will have a large fraction of the open time. So it's very important to be prepared to use CTA effectively at the beginning, because then we will be able to produce very interesting results. So far in Chile, the Chilean participation in the CTA consortium is about 30 scientists and engineers at 7 different universities, which are listed here. And we are working or trying to work on different subjects. We are actively involved in the modeling of astrophysics and particle physics, the galactic center, dark matter, tidal disruption events. And we are also involved in software, particularly at the Universidad Santa Maria in Valparaiso, and in the array control and pipeline software. And there is interest and the attempt to do some atmosphere modeling and atmosphere monitoring, as well as in the future multi-wavelength observations relevant to CTA. So we expect to become more and more involved in this, and we are interested in forming a larger group here in Santiago, Valparaiso, and other places in Chile to work towards CTA. So the conclusions, I agree with Farinaldo, exciting times ahead in astroparticle physics, so it's a good time to get involved in this. People are welcome to contact me if you want more information about opportunities to work here in Chile or collaborations with us. And you can find more information about CTA on the CTA website and on in the recent Science with CTA document, which is on the archive. Thank you very much.
Thank you very much, Andrea. So we have comment. Yeah, it's very amazing what is the future for CTA, for all the gamma ray astronomy. We have some questions, but maybe I can make you some now and later in the roundtable and all. But one of the questions that is asking Nicolás Mesa Retamal is, what is the expected angular resolution for CTA?
I guess maybe Germán answers that. It is energy dependent, but do you remember the numbers?
Well, I think it's around the arco minute or something like that. I remember at least it's better than Hess, but I'm not quite sure.
And it gets better at higher energies. It's worse at lower energies.
I think it's 0.1 degree.
Yeah.
Sorry?
0.1 degree.
0.1
That sounds right, yeah.
Fernando is saying 0.1 degrees. Yeah, another question, because it's also related with what you were showing, that it's very challenging for all the related of the computational level. So Nicolás Mesa is also asking, what is the speed of CTA process data? I mean, it's usually very challenging for the maybe how Chile participates in the data processing.
The rate at which it produces data, that's also a number which I don't have in my head, so I don't know.
Yeah, but I guess CTA it's going to be one of the largest observatories in the amount of data that it will produce, no?
Yes, it will be producing a huge amount of data. So it is being discussed how much of those data will be processed on site and here in Chile, and how much of the processing will be done abroad in the countries that are putting most of the money into CTA. But no, I don't really know the number. So I don't know whether Farinaldo knows or Germán.
Well, there is one thing the question is, what is the speed of CTA processing data? At the moment, there is no automatic pipeline for processing the data in CTA. It's something that is under construction. Then it's very...
Well, but I guess the relevant question is at what rate CTA will be producing data, because you have to process everything you produce. So yeah. We will have to get there up somehow.
Yeah.
But I don't know what the number is.
Yeah.
No, but also you were saying that I mean, one of the stuff that Farinaldo in his talk was saying, and you also were confirming, that is all the CTA and the quest of dark matter in general is very interdisciplinary. So there's going to be a lot of opportunity also for data scientists or people working in big data also. So related with this stuff, with the technical details of how much data is going to produce CTA. Yeah. So maybe we can continue with the. Thank you, Andreas. We're gonna then come back with all of the rest of the questions because in the roundtable. But now we can give the next speaker. This is going to be José Basso from Pontificia Universidad Católica del Perú, and he will be talk about the alpha magnetic spectrometer. So, José, whenever you want, you can share screen. Hi.
Okay, hi. So thanks for the invitation. Just to mention that I used to work in AMS while I was a postdoc in Italy, but there is one group in Brazil led by Manuela Becchi that they're also involved in AMS. So I'm going to talk about this. Just let me share the screen. Okay. Good. I hope you can see it.
Yeah, you can see it.
Well, so in general, AMS is looking at cosmic rays, charged cosmic rays, even though there was small publication about gamma rays, but mainly charged cosmic rays. So at the energies between GeV and TeV. As you can see in this plot about the fluxes of the different particles, so it's mainly protons, what it's been possible to see, but then if you remove these protons, so if you consider it as background, then you will get electrons, positrons, and also antiprotons, and we are looking for also different other particles. So the advantage of being in space is that you don't have the atmospheres, and it's easier to identify particles or antiparticles. You get a precise measurement of the energy and a high proton separation. However, of course, since you are at the space station, the detector has to be smaller, so you have a smaller effective area, and well, the lifetime will depend on the status of the detector. In general, there are right now 14 countries involved, 46 institutes. As I was mentioning, there was one in Brazil. We here in Peru were not directly involved. I was there. It was launched with the Space Shuttle Endeavour in 2011, May. So now it's been there for more than six and a half years in the space station. So since it's on the space station, it's orbiting Earth every 93 minutes at an altitude of 400 kilometers. So far, it's more or less more than 107 billion events. And then in the lower plot, you see the Payload and Operation Control Center at CERN, where the detector is monitored and the communication with NASA is 24/7. So it's not one big detector, but it has some sub-detectors, like a very small particle physics experiment. Here you see all of them. At the top of the detector, there is one layer of the tracker, but then you have one of the main sub-detectors that helps to identify protons or from electrons and positrons. So it's the TRD, the transition radiation detector. And another thing that also helps us to identify, separate positrons from protons or electrons from protons is the electromagnetic calorimeter, which is at the bottom of the detector, so the ECAL. And in the middle, you have TOF, which helps for the triggering system, and then several layers of the tracker, which in conjunction with the magnet can give us the, well, with the magnet you can have the directions of the sign of the charge and the momentum. And there is also reach, which helps us to measure the charge and the energy of the particles. So as I was saying, one of the main things that we have to do is to separate the background of protons from what we want to measure, for example, positrons and electrons. This is done with mainly two detectors, the TRD and ECAL. Here you can see both of them. In the case of TRD, you have positrons or electrons, which are lighter, and the transition radiation probability is inversely proportional to the mass. So that's why you get more radiation from positrons. And if you gather all this information, you can create some likelihood for proton background and for the signal in this case, and you can separate them nicely. And then we're using the electromagnetic calorimeter. So you have different also signals in the LED, larger shower for positrons or electrons in this three-dimensional configuration. So if you take into account also all these parameters and you mix them together in a multivariate analysis like a BDT, boosted decision tree, you can also separate electrons from positrons. And here you can see one event, as an example of one event. This is a 1 TeV electron, starting at the top, one of the layers of the tracker, then it leaves a signal in the TRD, then the top, more layers of the tracker, also in the reach, and in the electromagnetic calorimeter, which measures the energy, in this case, 1 TeV electron, just to give an example of the data that we have used. AMS has had the different publications and PRL, starting with the positron fraction. The positron fraction is just the number of positrons divided by the sum of positrons plus electrons. The first one was up to 350 GeV, then we went to 500 GeV. There were also publications about the electron, positron flux, together, protons, helium, antiprotons, boron, and carbon. And there are others coming in the next month. So about the anisotropies or time variations. So now what is concerning us, so dark matter, what we see, for example, in this case, you can see a plot of the sum of the positrons and electrons, so the sum of both particles, the particle and its particle flux, and the data from AMS will be the blue dots. Now you want to fit these dots with some theories. So you start with what we know basically from astrophysics. So you have electrons from supernova remnants, and then you will have some positrons coming from interaction in this interstellar medium. So then you will have, for example, the light blue curve for electrons, which is the highest one, and then smaller one contribution from positrons. But still, if you add those two things, you are missing something that we are seeing in the data. So that would be the green curve. We call this, in this case, a common source. Now the question is this common source coming from dark matter, coming from pulsars, coming from other sources? And that's the question that we have to address. You also can see here the separate fluxes for electrons. You see the contribution from this source, common source, is smaller compared to the diffuse flux. And in the case of positrons, it's a larger, much larger contribution, especially at higher energies. Now, as Farinalo was mentioning in the first talk, you can have dark matter annihilation, and in this product of this annihilation, you will have positrons, antiprotons, and other particles. That is what we are measuring. So now, if you want to explain the data that we are seeing with AMS with dark matter, you can postulate a dark matter candidate, for example, in this case with 1 TeV, the mass of the dark matter candidate, and then you can fit the positron flux and also the positron fraction. As I mentioned, the positron fraction is the number of positrons divided by the sum of positrons plus electrons. And you see that it is nicely fitting. Another thing that will be necessary in the case of dark matter is this isotropic distribution, and also you have to fit the antiproton spectrum. Here you see the ratio between antiprotons to protons, and using another explanation with dark matter, you see that it fits. You have the normal collisions producing antiprotons, but still there is something extra that we're seeing that could be due to dark matter, so dark matter annihilation. However, well, in this case, the antiproton contribution is not so easily explained by pulsars, but you can postulate different alternative models to explain this extra excess in the case of positrons and antiprotons. So, for example, you can say that there are pulsars of pulsing radio magnetized neutron stars. You can fit the results of AMS also with this. Or you can say, for example, there are supernova remnants producing also antiprotons or fitting the positron fraction. But even you can find some papers. Well, at the time of the first publication of AMS, there were more than 200 papers trying to explain these results with different theories. So in this case, for example, it's a modified cosmic ray propagation. So just by secondary production, you can also get the positron fraction. Now, the thing is that with the data that we have so far, it's not so easy to distinguish between different models. So we have to wait still some more time to gather more data. So in this case, it was done some time ago, but by 2024, we will get enough data, for example, to separate between models caused by pulsars and some from dark matter. You can see here 2 examples explaining the positron fraction and the positron flux, and then you see the points with the, so this is expected number of events given some of the models, and with the error bars given the statistics and the systematic errors, and you'll see there the models produced by pulsars are different from those that are due to dark matter. So this you could see in some more time gathering more data. Then there is also the anisotropy, which is still something that they are doing and will be published soon. And the current value of the anisotropy is compatible with both pulsars and isotropy. So again, we have to wait still for some time to see if there is a real anisotropy or not. So in conclusion, well, you want to know more details in general about other results from AMS, you can see this link, but then we have to wait again for some more data to be able to distinguish. But there is a dark matter explanation from what we have observed with AMS. Thanks.
Thank you very much, Jose. So one first question that we have here from Farinaldo, in fact, is asking, I mean, it's the question that everybody wants to know. How long is going to be AMS still running? Because, I mean, it has been in space at like 5 years at least, or more, maybe.
6.5 years. Well, still running, and we hope that it will run for longer time, at least the time of the International Space Station. Of course, there have been some problems. I think I cannot reveal much because, well, I'm no longer part of the collaboration, but still I have some insights, but still working, and we'll be gathering more data, and there might be some other EVAs, so extra vehicular activities to help it go further.
So,
I
just have one comment. So I just heard a rumor that AMS has been already funded for 10 more years. So I just wanted to know if that's true or not.
Well, that about the funding, I'm not so involved anymore, but yeah, this detector is still working, and I'm sure that they will get the money. So there's been a new film about Professor Team getting the detector to the International Space Station, Flight for Flight, if you want to see it from NASA. So I think there is no problem with getting funding. I think it's just that it should keep going on. But as I said, so we gather more data by 2024 or something like that. At least from these models, we could tell apart if it's dark matter or pulsars or something else.
Mm-hmm. So, I mean, we have another question, but I don't know how long it could take. But anyway, I'm going to ask it to you. Jorge Diaz is asking, how much does the Earth magnetic field affect the measurement on board of the space station, and how this is corrected in AMS? If the Earth magnetic field has an impact on AMS itself?
Well, for example, when it goes through the South Atlantic anomaly, then we get lots of data, and we just don't use the data when it's in the South Atlantic anomaly. And then there are some, of course, corrections for the lower energy events but at higher energy, what is important for us, not such big of a deal. And of course, if you want to go to solar physics at lower energies, then you have to take into account the geomagnetic cutoffs and everything. But so that's the effects of the solar activities and everything. It's below 10 GeV. Well, some say below 100 GeV, but actually you only see those effects below 10 GeV.
Mm-hmm. So yeah, in fact, this is one of the nice stuff of AMS. Also, it's very interdisciplinary, interfield, let's say. People that want to do solar physics, cosmic ray physics, dark matter, or another type of astrophysics, everything can be, I mean, not everything, but there are a lot of fields that have a lot of interest in the observation that AMS can do.
Yeah.
Yeah, it's very interesting. So maybe we can continue with the question, but in the round table. So thank you very much, Jose. So now we are going to pass to Sergey Kovalenko from Universidad Federico Santa Maria. Sergey, are you there?
Can you see the slide? Yeah.
Yeah, you can see the slides.
Okay. So thank you very much to the organizers for this opportunity to present the Andes Lab project. It is still a project. In this context, Andes is short for Agua Negra Deep Experimental Site. The idea is to construct an underground laboratory first in the southern hemisphere and the third deepest in the world. Inside the Agua Negra road tunnel, which is going to connect Chile and Argentina in around 10 years, optimistically. This project was proposed by an international team of scientists from Argentina, Brazil, Chile, and Mexico. Javier Bertu from Bariloche is the chief coordinator, and there are national coordinators from each country. The Agua Negra tunnel, first of all, the tunnel. Okay, this is a strategic, very well economically motivated project due to growing trade of Argentina and Brazil with the Asia-Pacific region. Currently, the transport connection between the countries is realized via several high mountain passes. Agua Negra Pass is one of them. All of these passes are heavily dependent on the weather conditions and suffer severe cuts in winter due to snow. The obvious solution, of course, would be to drill the tunnel in the mountain range and construct a corridor between the west and east of the continent so that the goods would be transported through the tunnels towards Chilean ports and then shipped further. The total estimated cost is about more than $1 billion. This is an estimation, and with the tendency to rise, of course. This is a geographic location of the Agua Negra Pass and the future tunnel. And it will connect the Coquimbo region from the Chilean side and San Jose province from the Argentinian side. The tunnel actually this consists of two tunnels, one directional, two-lane road tunnels, 40 kilometers long, 12 meters of diameter, separated by a distance of 60 meters. The laboratory is planned for installation in the Chile-Argentina branch, in the deepest point of the tunnel, which is about this depth, and which amounts to 4.5 kilometers of water equivalent of rock overburden, which would make the laboratory the third deepest underground laboratory in the world. The location of this deepest point in the laboratory is at a distance of 3.5 kilometers from the Chilean entrance, and 10 kilometers to the Argentinian exit. This is a schematic layout of the laboratory. It is typical for the underground laboratories of this scale. It contains it is going to contain two halls, main hall and a service or secondary hall with these dimensions, 50 meters and 40 meters long, 21, 16 meters wide, and so on. This is a cross section of the halls with the human figure for the scale. there will be also two pits for installation of large detectors. This is a large pit, 38 meters depth and 30 meters of diameter, and another small ultra low radiation pit for some experiments, very low background experiments. And this big pit, I forgot to comment, is conceived for installation for hosting of a big liquid scintillator neutrino detector, akin to CAMLAND or Borexino detectors. So this is a layout. There are several places for smaller size experiments, like for applied physics. There are two support labs envisaged in this project on each side, in La Serena and in Rodeo, Argentina. The idea or the hope is that these labs and nearby universities mutually benefit from collaboration with this laboratory. Now, the question: why do we need to go deep underground? Mainly due to cosmogenic muons, which are produced in the atmosphere by cosmic rays and produced appear in the case of charged muons. The hadronic component of the shower could be easily screened with a few meters of concrete overburden, and while muons and of course neutrinos are capable to penetrate very deep underground. At sea level, the flux of muon flux is about 100 counts per square meter per second. Why these muons are so unwelcome? Because of muon spallation reaction with an environment, with the nuclei of the surrounding matter, in which in this reaction there appear abundantly neutrons, and these neutrons are the principal background for the direct dark matter detection via elastic scattering on the nuclei. So this is a reaction of direct dark matter detection, and neutrons could easily mimic this reaction in an elastic scattering, producing a similar nuclear recoil. Nuclear recoil is what is detected in this sort of experiments. That's why the underground labs searching for such processes, very rare processes, should be installed deep underground. The flux is a decreasing function, exponentially decreasing function of depth. This is a curve of the muon flux versus depth in terms of kilometers of water equivalent of rock overburden. So the deepest lab in the world is Jinping in China. Then follows Snow Lab in Canada, and Andes with its 4.5 kilometers of water equivalent. So this is a list of underground running underground existing underground labs. There are small underground labs. Andes underground labs is going to situate in between Stanford Underground Research Facility and Snow Lab. What is special about this lab, about the Andes lab? Its location. As you see from this map, all of the existing underground labs are located in the northern hemisphere. So the advantages of the Andes lab, the first advantage is its location in the southern hemisphere, which has opposite weather-induced demodulation of the signal, possible modulation of the signal. and which is important in view of the claim of Dama Libra experiment on the detection on observation of annually modulated dark matter signal. And another advantage is that it is third deepest in the world. There are various other advantages, mainly for neutrino experiments. Its remoteness from the reactors, neutrino reactors, and then low reactor neutrino background, and so on. As to the scientific program of the lab, it is too early to discuss anything definite, because this field is very dynamically evolving, and in a couple of years, or in some near future, its status may dramatically change, of course. But nevertheless, there are a bunch of possibilities discussed by the collaboration. Among them, to host a large Latin American neutrino detector, liquid scintillator detector, neutrino detector of large scale in the pit and large pit, which I mentioned before. Double beta decay, neutrinos double beta decay experiment. These two sort of experiments are typical for nearly every existing underground lab. Some experiments for applied measurements, and of course dark matter search experiment. Currently, the most attractive among the most attractive possibilities, there is the idea to host a clone of Dama Libra experiment in this laboratory in order to disentangle dark matter annual modulated signal from the weather-induced seasonal modulation, and ultimately confirm or refute this claim of Dama on annual modulation of the dark matter signal. Organizationally, this laboratory will be managed by a Latin American consortium for underground studies, CLAS, which currently includes 4 participants formed by 4 countries: Argentina, Brazil, Chile, and Mexico. And as far as I know, Colombia also expressed its interest in participating in this this collaboration. Summary. Andes is a unique opportunity for deep and large underground laboratory in the southern hemisphere, with various advantages, scientific and educational advantages. It received strong international support and interest from many, and international experimental collaboration. Consortium CLAS offers additional opportunities for integration of Latin American science. And the expected commissioning of the lab is in 10 years, optimistically, of course. And more information could be can be found at this site. So, thank you.
Thank you very much.
Yeah.
So I guess we have one question. One from Farinaldo. Maybe Farinaldo, you want to ask him?
What happened?
Yeah. So one of the things that I wonder is why we haven't pushed for a scientific paper regarding UNS, because I think this is missing the literature. We have done this in the past for Fermilab, for Snow Lab, and many other, and even experiments such as Dune. They pushed for a paper before even they built, and they got the experiment approved. Shouldn't we do the same?
You mean Anders Lab?
Yes.
Yeah, I didn't get your question actually. What should we do? It is still on the way. It is not yet, unfortunately, approved completely by the Chilean government. It is on the way. So we should wait. But there four workshops were organized in the last years on the subjects of on the scientific program of this
Yeah, but
So,
I mean, not even the workshop. I mean, for instance, if you do an Inspires search with the title Andes,
you mean?
you find 11 papers, which out of these 11, there are like 2 which are real papers. So maybe if we had a paper describing what kind of physics we could do, I'm sure that will trigger lots of following
Maybe,
studies
maybe,
what we
yes.
could do on this
Yeah.
and on.
You mean on the scientific program of this lab, this construction? Yeah, maybe. Well, but we should probably discuss this. There are proceedings, actually, of the workshops which are published online, not in Inspires. Yeah, but, okay. Okay, no more comments. Okay, it's a good idea, but I cannot comment more.
Yeah. Now maybe later in the roundtable we can also expand a little bit.
Yeah, sure.
Yeah, thank you very much, Sergey. We are gonna continue with the program because the time is passing fast. So the next speaker is gonna be Rogério Rosenfeld from UNESP in Brazil, and he will talk about the dark energy survey. Please, Rogério.
Okay, can you hear me?
Yes, we can hear you.
Can you see my screen?
Yes, we can see your screen.
Okay, so thanks for the invitation. I'm going to talk about the Dark Energy Survey for the Dark Matter Day. To tell you what the Dark Energy Survey is, it's a large collaboration of 300 scientists around the world. And so we have a Brazilian consortium that is participating in the collaboration. It's led by Fermilab, and the director now is Josh Freeman from Fermilab. So what we want to do in terms of science, we want to use 4 different observational probes of dark energy. So we want to study large galaxy clusters and the statistics of galaxy clusters. We expect to have tens of thousands of clusters up to redshift of 1. We use also the weak lensing, these distortions of the shape and magnification of galaxies, and that has information about the matter distribution. Use baryon acoustic oscillations, or if you want the correlation function of galaxies, which has this feature. And so we're going to use 300 million galaxies, also with Z redshift up to 1 and beyond, and also supernova. And one thing that we want to do is to constrain or get more information on the dark energy equation of state. So if you have a very simple parameterization like this one of a 2-parameter W0 and WA, for the W of A is the relation between the energy density, the pressure and the energy density of this fluid, which we call dark energy, which is responsible for the accelerated expansion of the universe. This is the type of forecast that we have for these 2 parameters. And so this is just a forecast, and one thing that's important to notice is how much do you gain by combining these different probes here. So just to tell you that the project is based in Chile, and the CTIO, actually not too far from the place where the tunnel is supposed to be built. Yeah, so it's close to La Serena. So it's actually the same road that leads to the tunnel, the Aguas Negras tunnel. Actually, I forgot to mention that the next workshop of the Aguas Negras, the Andes project, is going to be here in São Paulo, August next year. So this was just a parenthesis. So so we use this old telescope here, which is called the Blanco telescope. It's a 4-meter telescope. It has been refurbished in order to be able to have this camera here. So this is what we call a dark energy camera. This is the Blanco telescope, and all the support was built in order to hold the camera, which is it's a 4-ton camera. And so this camera here is a CCD camera with 590 megabytes, and is able to see light from more than 100,000 galaxies up to 8 million years light years away in each snapshot. So this is just the array of the CCDs, and just having an idea of the resolution. It's really good resolution. I couldn't refrain myself to show this. This is the dark energy camera picture of the famous gravitational wave event of neutron star fusion. This is the optical counterpart. So it's the first optical counterpart of a gravitational wave event. And with this, one can even estimate, with one event, you can estimate the Hubble constant because you know all the parameters of this thing. So in terms of dark matter, I think one of the major contributions of the dark energy survey was to identify new dwarf galaxies. So we discovered 17 new dwarf galaxies, and 27 were known before dark energy survey. And there was a fundamental contribution from our team, especially from Basilio Santiago's team from the south of Brazil. And there was a joint paper with Fermi-LAT, because Fermi-LAT was targeting these dwarf galaxies because the dwarf galaxies are dark matter rich, and hence the idea was to get bounds from indirect dark matter searches. And one of the conclusions is that WIMPs, thermal WIMPs with masses less than, say, 100 GeV are excluded, but of course there are some assumptions if they're thermally produced, and the BB bar modes, I think I have a, oh sorry, this is just how the cumulative number of dwarf galaxies. So you can see how much the DS has contributed to this. And this is a plot of recent results, not so recent anymore, but last year results of Fermi-LAT and DS using 45 dwarf Milky Way satellite galaxies, which are rich in dark matter. So what you see here is the cross-section in the y-axis and the dark matter mass in the x-axis. And what you can see is that if you want, and this is in the BB bar channel, and if you want the dark matter to be a thermal relic, you exclude dark matter masses below 100, say more or less 100 GeV. So this is something important. So one thing that's also nice is that when you study the galaxy power spectrum, the distribution of galaxies in the universe, the Fourier transform of that, it's sensitive to new physics. In particular, it's sensitive, it could be sensitive to the mass of dark matter. So if you have instead of cold dark matter, you have warm dark matter, what happens is that you have a suppression in the power spectrum just because of the free streaming of this warm dark matter. However, don't get too excited about this, because this is a linear power spectrum, and at these scales, nonlinear physics is very important. And if you take into account nonlinearities here, this effect is almost washed out. I have a student, Jessica, who is working on this, and unfortunately, you lose much information, at least at small z=0, but in this observable. So this is bad news. I think the dark energy survey will not be very sensitive to the mass of dark matter. And now I'll finish just saying some cosmological results from the year 1 data. So we have an area of 1,300, approximately 1,300 square degrees, which is approximately 1/5 of the survey area. And we have combined 2 cosmological probes, so the galaxy clustering with the weak gravitational lensing. We have more or less 26 million source galaxies and 605,000 lens galaxies. So we combine observations from this weak lensing probe, so just the distortions of these galaxies, and also the 2-point correlation function of these galaxies, and also mixed observations. So this was really first time this was done in the same experiment. I forgot to mention that the dark energy survey does not measure redshift using spectra, but measures redshifts using filters. So the redshift information is not very precise, and but we gain in terms of how many galaxies we can observe. So I showed you some of the results that they were published this year, not too long ago, a couple months ago. First of all, the cosmological parameters that we analyze is the amount of matter in the universe, the amplitude of the scalar fluctuations, the index of the scalar index of the power spectrum, the amount of baryons, the Hubble constant, the contribution of neutrinos, and the equation of state. So these are the cosmological parameters, but there are also other parameters which are related to modeling in this in the framework of DES. So we need to model bias and redshift uncertainties. So there are many parameters, we call them nuisance parameters, and the covariance matrix is also not easy to estimate, but this is the results that we have. So this is amazing, I think, because this is omega matter and something that's related to the amplitude of fluctuations at the scale of 8 megaparsecs. And what you can see here is the results from DES in blue and Planck in green. And the amazing thing is that the areas are not very different. So it's the first time that a survey of galaxies is giving results which are comparable to Planck results. And it turns out you can combine the two data sets and you get the most precise values for omega matter and this parameter S8. Now, this is in the context of lambda CDM. Now, if you want to get constraints, so we can go one step ahead and one step forward, and also constrain the equation of state for a constant equation of state. So there's one extra parameter, and that's what we get. So this is just what you see here is the equation of state parameter, constant, and this is the result for DS only, but you have to look at DS plus Planck plus BAO plus supernova, which is this red thing, the red curve. This is the PDF for finding the equation of state, combining all possible data. And the result that we get is minus 1.00 plus or minus 0.05, basically. So the sentence that goes with this, that when we first found this, Scott Doddleson wrote, "There goes the Nobel Prize," because we are just confirming lambda CDM. So this is, I think this is all I had to say. DS is finishing its 5-year data taking, and so next February is going to be finished. Maybe there will be 6 months extension, and the analysis for the year 1. So this was all based on year 1, and we're starting the analysis on year 1, 2, and 3. So this is all. Thank you.
Thank you very much, Rogerio. So what? I mean, I don't know if there are questions, but one of the nice stuff of DS, because just to the public that is listening, watching us now. So DS is giving another information that we were not discussed before with the other talks. That is how the structure formation is going, no?
Right.
And the history of the universe.
That's right. That's right.
And the importance of dark matter in all this, of dark energy as well.
Right. Right. So we are sensitive to the total amount of matter in the universe. This omega m. We're sensitive to fluctuations in the matter in the universe, the sigma 8 or S8. And we're not, unfortunately, not very sensitive to the properties of dark matter at this point. And also, I think the main contribution, as I said, of the dark energy survey to dark matter is the discovery of dwarf galaxies, satellite galaxies of the Milky Way, which were then targeted for the indirect detection of dark matter.
Mm-hmm. I don't know if there are other questions, just because we were just talking about dark matter and dark energy, and in fact, here behind me, I have, in fact, these two, this is dark energy, these particle zoo puppets, I mean, plush toys, and also I have the dark matter, because today is the day of dark matter, so today we're talking about this guy. So let's, I mean, just a break. Okay, so we are gonna go now, I mean, let's keep the question for the round table, but let's go now to the last talk, that is Juan Carlos. He's gonna talk about the embodied simulations and the role of dark matter in that. So Juan Carlos, if you are there.
Yes, I am.
Yeah, hi.
Okay.
Hi, give me one, please. I will share the desk. This one. Oh, this one. So, sorry, we'll give you the back because the microphone is just here. Thanks to organizers for letting me, giving me the opportunity to talk here about this issue concerning to one of the ingredients or one of the key ingredients we use to study the dark matter in the universe, which in principle is this technique of using dark matter simulations that we actually use for many different things, from detectable or modeling detections of dark matter signal, or to study the large scale structures. So in principle, observations suggest that around 25% of the energy density content of the universe is in the form of mass. Around 80% of that mass is in the form of dark matter. This means that in general, the density field in the universe is dominated by the presence of dark matter. The way it distributes and it behaves like we see here in what we know as the cosmic web, when we have the distribution of mass in filaments, halos, and voids, which is the common or the regular pattern in which nonlinear structures organize because of the presence of gravity, is the common thing we see when we go to the telescopes and study the distribution of mass. Actually, what we do when we go to the telescope is to study the distribution of galaxies. Galaxies, we believe they form in the very deep region of the potential well provided by dark matter halos, which we are going to assume are just the peaks of this mass density field. So for us, talking about dark matter and the distribution of dark matter in the universe will be very closely related to the way galaxies are actually distributed in the universe. And we already saw it when we were talking about, in the previous talk, when they were talking about the dark energy survey. So the question is, if we want to really understand the nature and the properties of dark matter, we actually need to know also the way it is distributed in space and in time. We need to be able to solve the question about how is the mass, the dark matter distributed in the universe, in any place in the universe, at any time in general. In order to ask this question, you have, of course, to write down some stuff. And one of the, in principle, one will say easiest thing is to use linear approximations. What we see here is what we get as the linear growth equation, what we get when we use perturbation theory to study the growth of density contrast or density fluctuations in the mass density field. In general, if we want to study the density distribution, we can focus just on the regions where the contrast is, because on the regions where the contrast is are the regions, the places in the universe where the interesting stuff is going on. The point is that this thing is just an approximation that doesn't work in general. And in principle, we cannot use it to explain, for example, the behavior and the growth of dark matter halos and galaxies as we see them today in the universe. And it is actually, in any case, difficult to solve, even in this case, the analytic form, because we have to consider always the behavior and the interaction of the matter with expanding the cosmological background. So in general, what we do when we want to solve this problem from the very, very beginning for any general case is to use embodied or cosmological simulations. Actually, what we do is to map this continuous density field to phase space. In phase space, we cast the problem as a problem in phase space for the distribution function of particles in phase space, where we can use then a Monte Carlo approximation, where we then sample the distribution function in particles, and we solve the equation of motion for each of these particles, intending to provide a solution for the motion of the different set of particles in the volume. In this way, we cast the problem from the continuum of the mass density field to the issue we know as the embodied problem. That's what we have here. We have here a common image of the evolution of a piece of the universe. For all of us, the universe is cubic. Is the easiest way to impute, for example, the cosmological principle through periodic boundary conditions. And we start from
very homogeneous initial conditions with small perturbations provided by the linear theory and observation from the density contrast observed in the temperature fluctuations in the CMB, and then we let the particles evolve in the expanding background, with the interaction, with the gravitational interaction among them, and then gravity does the work, and then the structures appear, and the filaments and the halos and voids appear. And then in those halos, we hope to be able to form galaxies. All we are familiar then to this kind of nice slices of these huge embodied simulations where we actually try to mimic the distribution of mass then on the large scales. And we end up having these kind of features like dark matter halos, where inside of a halo you have more dark matter halos that in principle should have or should be hosting galaxies. Yeah, but that's what we should see in the universe if we were able to look at the universe looking at the eyes of the dark matter. One of the interesting and at the same difficult things when you are doing simulations are the issues associated with the limitations of the numerical approximation, the embodied approximation, and the technical limitations you have when you want to run the simulations. One of the technicals and at the same time theoretical limitations is that we need to constrain the simulations to a given resolution. We would like to have as large resolution as we would like in the simulations, but the resolution, which in principle has to be with the number of particles you use to track the density field, is not unlimited. The larger the number of particles you use, the larger the computing power you have to invest in order to be able to solve the problem. The point is that if you use a larger number of particles tracing the density field, you will be able to recover with better detail the properties of the density field, the density function in the phase space, but also you will have the opportunity to resolve very much detail on the physics happening in the piece of the universe you are simulating. Also, if you don't only focus on the behavior of dark matter, but also try to model more complex physics, which is happening there, which is related basically to the way dark matter interacts with baryons, you will need to make the things a little bit more difficult, introducing then the physics related to the baryons that we will see play an important role when we want to see the observable things which is the thing we do when we do our experiments. Another issue is that we have to be able also to run large enough simulations, not in the side of the number of particles, but indeed in the side of the size of the piece of the universe you are using. The larger the box of the piece of the universe you simulate, it will provide you with better statistics and a better information about the cosmological context you try to use. Here we see a trend of the evolution of the simulations in the last few years, where we are trying to go in the direction of increasing the resolution of the simulations without losing the statistics we can get when we run in better conditions in box sizes. The ideal actually will be growing the curve in this direction, the opposite direction, but the larger the box, the larger the number of sampling particles you will need to use, and indeed you start to lose resolution when you don't play it in the right way with the numbers. So the bet in the last few years have been increasing the number of particles while reducing the size of the box in order to be able to recover the more complicated parts of the physics behind the phenomena. As all we know, dark matter cannot be seen. All we can see, as I already mentioned, is the galaxies. So when we run the simulations, we build this kind of maps with the distribution of the mass in the very large scale, where we see the halos, the clusters of halos or clusters of galaxies, and the filaments connecting those structures. But we actually see the stuff which is forming inside, which is this thing, the galaxies, as the result, for example, of this TNG simulation from the recent Illustris simulations. So once you run the simulation, all you have to do is to try to pair the results of the simulations with the stuff you can see, with the observable you have, which in this case are the galaxies. things doesn't work that good in that direction when you do the stuff. For example, this is an old result of the, not the first simulation, but the one of the things you can get, and actually you can get wrong when you try to analyze the results of the simulations when you compare them with the results of the observations. What we see here is a comparison between the abundance of subhalos hosted in a dark matter halo, similar to the dark matter halo of galaxies in the local group, Milky Way galaxy and galaxy Andromeda galaxy. What we see here is the abundance of substructure, dark matter halos hosted in that dark matter halo, which in principle should host a satellite galaxy. And what we see here with these points is the result of the observation. In principle, what we have here is the result of dark matter only simulation. No baryons, no gas at all has been included in these simulations. And in principle, the result is the thing we already know, the problem we already know, which is already called the problem of the missing satellites problem, in which dark matter simulations produce or predict an overabundance of satellite galaxies, which is of the order of a factor of 10 compared to the stuff we get when we go to the observations. One has to stress that this is not only a problem associated to the substructure. It is also, for example, we can see the same problem when we go to the field galaxies in the local group. Not only studying the satellite galaxies in the Milky Way. Solutions, possible solutions to this problem. There are many. Actually, this problem is very interesting because it opens the door to many different situations where we could have different physics playing in the game and provide an interesting scenario to solve the problem in many different ways. For example, this is the result of a very recent simulation where the formation of dark matter halos with structures and mass similar to the mass of the Milky Way halo has been performed, but in this case, including the effect of the formation of the galaxies in those halos. That means the baryon physics has been turned on in those simulations, and the star formation and feedback recipes have been introduced. When you do such a thing, you produce abundance curves like the ones you see here in green and pink curves here in the corner of the plot, where you see, comparing with the points, which are the results of the observations, that when you turn on the baryon physics, you can actually, in principle, solve the problem of the missing satellite problems if you do it right, if you do it in the proper way. The point is that we don't really know which is the proper way. I mean, we are kind of tricky, tuning parameters, doing tricky things here. With these simulations, we kind of tune parameters in order to be able to reproduce, for example, this thing, the abundance of satellite galaxies in the Milky Way halo. But however, when we fix the parameters to fit the data in this region, we miss, for example, the abundance of field galaxies in the local group, which is the stuff we see here. We see here in this solid curve the abundance of galaxies when you have only dark matter only simulations, and here in blue we have the abundance of galaxies in those simulations when you have already included the physics in the same way you use it here to solve the problem we had already for this thing. So in principle, we think that many things have to be learned concerning to the physics we put or we plug into these embodied plus hydro simulations when we try to understand the results of the formation of structure. And this is the moment where we are already getting close to it, but already not there in order to solve all the problems. Another possible solution will be, let's change the nature of dark matter. Let's suppose that dark matter is not cold dark matter, but it is warm dark matter, hot dark matter, or mixtures of those. An example of those tests is shown here in this slide, where we show the results of the cold dark matter simulations, Aquarius simulations, and an equivalent dark matter simulation where we are using a warm dark matter simulation. The changing the nature of dark matter, in principle, in this case, changing the mass of the dark matter particle, which in principle also will change the velocity dispersion of the particle, will suppress the formation of small structures and this will suppress the abundance of substructure in the low end of the mass function, as we see here, where we see a strong suppression of these small things we see here, like flies on a piece of cake. One of the possible solutions will be this thing, that not that we have the physics wrong in the baryon side, but that we don't know the nature of the properties of the matter, of the particle of dark matter, or in the end the solution will be a mixture of both of them, or many of those cases. Another issue concerning with the simulations is the idea of the nature of the distribution of mass in the very, very high density regions of the density field, which is the center of dark matter halos. It is important because the galaxies are forming in the first 10% inner region of the halo, and in those regions the simulations are not precise and are strongly affected by the effect of the collapse and the flow in and flow out of material because of the feedback of supernova. What we see here in this figure is the result of a cosmological simulation where baryons have been included, but where in the yellow region, we are highlighting the region where the numerical convergence is at risk because of two-body relaxation in the simulation. In these kind of simulations, two particles of dark matter could interact to each other and modify the trajectories, the path of each particle, changing the slope of the density profile in the inner region in an unphysical way. This is not physical, this is numerical noise in the simulation. So we shouldn't believe the results of the simulations in the very center. However, in the regions where we can believe the result of the simulations, we see that the interplay, the interaction between gas flowing in and out in the region where the galaxy is forming because of the explosion of supernovas, which is ripping out and moving the material outside the dark matter halo, and the gas cooling down and falling into the potential, in the inner region of the potential, well provided by the dark matter halo, modify the orbits of the particles, of dark matter particles, in a way that the original dark matter only simulation changed its density profile from this cuspy behavior to the chord behavior we see here. Results that this thing is important when, for example, we want to provide a forecast for the detection or detectability of dark matter annihilation in, for example, the galaxy. Here we see the maps of the eventual flux of gamma ray originated in the center of the Milky Way halo because of the self-annihilation of dark matter halos, of dark matter particles, sorry. The point is that all we know that in principle, then in the inner region of the Milky Way halo, the density is the larger and the probability of annihilation is larger where the density is the larger in the very center. However, since we don't know which is the effect of baryon in the distribution of matter in the inner region of the halo, we don't really know what should we expect about the signal of eventual annihilation of dark matter in the inner center of the Milky Way, for example, or from the full sky. I mean, in principle, we can make maps as the one presented here from the Millennium 2 simulations, where we could, in principle, try to forecast the detectability of annihilation from the neighborhood in the local universe, but still we don't know the impact of the baryons in those density profiles in order to see if these regions are indeed deep enough or have density contrast large enough to provide a detectable flux of dark matter particles. So there is a lot of work that has been done in this direction, but there is a lot of work that has to be done in order to be able to solve many of those questions associated with the numerical issues or the physics that we have to implement to be able to, in the end, be able to determine the way the matter is distributed in the universe. In the regions, we can actually detect any behavior of those or any evidence of the presence of these things. So many takeaway or take-to-home things from these simulations. Actually, they provide a lot of information, not only for particle physics, also for astrophysics and galaxy and large-scale structure things. But I mean, those simulations are expensive, difficult, but still very inaccurate. And we have still many things to do in order to be able to solve the problems from the side of the dark matter, from the side of the simulations. I mean, the good thing is that it is fun and it looks like there is plenty of space to plug many physics from the particle physics side or from the astrophysical side, as well as from the numerical point of view. And that's all I wanted to say about it.
Thank you very much, Juan Carlos. So yeah, let's, sorry, I'm gonna just enable this. Okay. So there are there are some questions that is for you that, like a takeoff, that is that how technical is the simulation itself? It requires a lot of resources, computational resources, no?
Yes, indeed. I mean, it depends much on the resolution you want to recover, but also on the physics you include or you introduce. If, for example, you want to run a high resolution Darmatter-only simulation, one of the largest simulations we have seen, which was shown in one of the slides, it took more than, it was like 1,500 million CPU hours just to run one of those simulations. The point is that if you include baryon physics on this thing, it will take until 20 or 50 times more time to run this kind of simulations, and it will require you more time in the cluster and more CPUs to do it. I mean, this kind of simulations usually run in thousands of CPUs, 10,000, 15,000 CPUs for periods of time of months. So the larger the resolution or the richer the physics you include on the problem will require you much better computational resources. In the end, it means more money you invest on it. Who's looking for hotel?
No, yeah. So, but all this, how is the, or maybe just to, maybe better we can pass to the round table. So first of all, we thank all the speakers. It was very interesting, and it's amazing to know all the different topics that it's been people working in Latin America. So we just put here a small sample. There are many more that unfortunately we cannot have all the people here, but yeah, this motivates us to continue with this stuff of the law physics. But we're gonna start with the round table. So I'm gonna start just continue with another question for Juan Carlos. How is the infrastructure itself is not, there is a small cluster or something like that in Colombia that you run the stuff, or you rely on external?
Yeah, with small scale facilities, you can run kind of successful simulations. For example, isolated galaxies or isolated Darmatter hills. But in Colombia, for example, we don't have the facilities to run such a large simulations. For example, we get access to Jülich Supercomputing Center in Dresden, where we have the opportunity to run with thousands of CPUs, this kind of simulations. However, I know, for example, in Brazil, there are this GMOJA cluster, for example, is available, and its facilities are competitive with the requirements one will actually like to use to run this kind of simulations in Latin America in the local neighborhood.
Mm-hmm. So in Brazil, sorry.
Yeah, in Brazil, I know there is there is a big cluster. I know it because they use it for geophysics and oil exploration, but it's called GMOJA. And I don't really know the details of the size of the facility, but as far as I know, is one of the largest clusters in the South America.
Yeah, I don't know if Rogerio knows about because I guess also for dark energy survey it requires a lot of computational power for the.
Right. So for the dark energy survey, right now we have our own cluster in Rio, which is in Rio. There's something called the Laboratório Nacional de Computação Científica, and it hosts several clusters, and our cluster is hosted there. I think the largest computer that we have there is called Santos Dumont, but I'm not sure how accessible that is. I think it is accessible if you make some project. And right, so this is what, so we are using our own cluster at this moment for our purposes. So maybe Santos Dumont also. I think there are some projects that they're being running Santos Dumont.
You're right. Maybe Santos Dumont has the largest facility, and I guess, as far as I know, those are the largest facilities placed in South America for this kind of jobs.
Mm-hmm. Yeah. Also, I remember that, if I'm not wrong, also in the university, in the Catholic University in Chile, there is a group doing by simulation, no?
Yes. Padilla, Nelson Padilla, and co. They actually work very hard in this kind of things. Also in Buenos Aires, I already forgot the name of the university. Patricia Teixeira is working also in this kind of simulations. And Cecilia Scanapiato is also back there since a couple of days ago, working in this kind of stuff too.
So maybe we can. I'm gonna check just some of the questions that there are still in YouTube. So one that we have from the very beginning for Farinaldo is from Axel Bonilla. Sorry?
I wanted to answer the questions that I was asked before, that I didn't know the numbers.
Okay.
So I was asked, what's the angular resolution of CTA? I looked it up in the Science with CTA document. Above 1 TeV, the angular resolution is 0.05 degrees. That's 3 arc-minutes, or better. It gets better towards larger energies, but at 1 TeV, it's about 3 arc-minutes. And the other question was the data rate of CTA, which will be about 10 petabytes per year.
Petabytes?
Petabytes, so that 10 to the 16 bytes per year.
Yeah, that's a lot.
Yes, it is a lot.
Yeah, it's amazing. Yeah, maybe I don't. I was Nicolas Mesa Retamal, the one who asked this question. So, thank you, Andrea. So, one was, in the very beginning, there were a question that we didn't ask, make it to Farinaldo, but was Alexander Bonilla, that if he was asking to him if he can explain a little bit a possible relationship between neutrinos and dark matter, even though there were some talk in the chat, but
but he was look, let me see if my microphone is on. Yeah,
we can hear you.
So he was actually mentioning to you about relic neutrinos, which are neutrinos from the CMB. Prior to CMB, so from early universe. So what happened is, the relation between dark matter and neutrinos is that, depending on how dark matter is produced, you can actually mimic the effect of neutrinos on the CMB power spectrum. So the neutrinos, for instance, relativistic degrees of freedom, they have an impact on the CMB. And depending on how dark matter, if dark matter is produced, let's say a fraction of dark matter is produced relativistically in the early universe, it can actually mimic the same neutrinos, the relic neutrinos that we all know. There are also other connections. For instance, if the dark matter interacts with neutrinos in the very early universe, might also determine when these dark matter decoupled from the plasma. So there's another connection with the relic neutrinos. So those are the two main connections between dark matter and relic neutrinos that I know of.
Mm-hmm. So okay, I guess for Alexander, it's okay. I mean, maybe if he has more questions, he can also comment here in the chat. So another question, but this is for the case of for Sergey. It's about Andes. Jorge Diaz was asking first if you know about this Andes very long baseline neutrino experiment proposal, and his question is, pointing a neutrino beam down to one side of the Earth to another is very challenging. And has any of the relevant labs like Fermilab, CERN, or JPAC officially comment about this proposal? You are mute. You have to unmute yourself, Sergey. We can hear you in the upper part.
Hello? Hello?
Yes.
Now we hear.
Yeah.
Okay. Well, but this is not a proposal, but one of the options for physical program of Andes Labs. But it is very difficult, very difficult to realize technically. Of course, for a very CERN and Fermilab are the laboratories, accelerator laboratories, which can produce neutrino beam in the beam dump experiments towards the lab, Andes lab. I have I don't remember precisely the distances, but it is very appropriate place. I mean, Andes for this sort of experiments. But imagine how to launch the neutrino beam in certain direction. Technically, it is very difficult to do. But okay, there is a proposal. No one discussed it in details and seriously, especially now when the Andes project has not yet been approved completely. So, but well, this idea exists. Yes, Fermilab and CERN are possible laboratories which may generate these neutrino beams.
Mm-hmm. And the type of physics in this case is going to be affecting matters, no? I mean,
yes,
matter affecting neutrino oscillations.
Of course. Yeah, of course.
Yeah. Oh, good. Because also this is another part that, I mean, there are many models of dark matter that requires a strong connection, let's say, between both with neutrino physics. That one is essential for the other. So any experiment that could help to see if there are deviations with respect with the standard picture of neutrino in which dark matter could be related, it would be very nice. So I have another question. So let's see. Well, I guess I don't know who asked this, but it's for Sergei. Australia is not supposed to construct an underground lab as well.
Yes, yes, I hear it. Even there is an underground under glacier. There is in the South Pole a laboratory, an experiment already installed. Dark matter, DM ICE-17.
Mm-hmm.
Yeah, at the bottom of the ice cube experiment, at the depth about 2.2 kilometers of the water equivalent, as far as I remember. Well, but it is still in progress in the data taking stage. Already reported some data about this annual modulation, which is the data consistent with no annual modulation, but they are still taking data. So in principle, there is a laboratory, but at the South Pole. But to repeat or confirm or refute, as I said, the result, this claim of Dama Libra, one need to definitely to do this in a definite way. One need to install a clone of this experiment, which is quite large experiment to install in some place in the southern hemisphere, like in Andes laboratory, and repeat this experiment. Well, in Australia, I know about this project, but I don't know about the present status of this proposal. Mm-hmm. I haven't heard anything definite, but I heard about that. Yes. No, and I cannot give more comments on this project.
Okay, so let's see. There is another question. I don't know if if people here in the Hangout want to start to a debate with, to talk, please be free to unmute yourself and ask questions to the other speakers. So, for instance,
one from Nicolas, I might answer that. From Nicolas Retamal, I guess. Mm-hmm. Hello?
Yeah.
Oh, okay.
Which one? About the
general question. So if there is an actual model that has been falsified with the non-detection of dark matter.
You want to answer the question, no?
Yeah, I can answer that one.
Oh, please.
So yeah, so there are not actually just one. There are several models, and there is also the statement has to be quantitative. For instance, models which use the Higgs, like in the standard model, as a mediator between the dark matter particle and the ordinary matter, like baryons, quarks, protons, has been excluded up to roughly TeV scale. The same happens with the dark matter talks to standard model particles through the Z boson. The Z belongs to the standard model spectrum. Has also been ruled out up to the TeV scale. There are combinations of those models have also been ruled out based on the latest results from direct detection experiments. Those are the two main ones, but there are also models which you have for instance, if you have a scalar also as a mediator, a new scalar, exotic scalar as mediator, if this scalar has masses around the weak scale, has also been ruled out. And there are many other models which, if you have a vanilla-like interaction, when I say vanilla means that I just saw if it's SUSY is ruled out. No, SUSY goes beyond the MSSM. So the MSSM, neutralino dark matter, just answering the question that popped up, a neutralino dark matter in the MSSM is basically ruled out. Okay, if you want to explain through thermal freeze out, dark matter, if dark matter is thermally produced, the MSSM is not a solution for it. Okay, there's just one case in particular, actually. It is if the MSSM, in the MSSM you have a Higgsino dark matter with a mass of 1 TeV. It's not 1.2, it's not 0.9 TeV. It has to be 1 TeV. And it's very fine-tuned. But then you can still obey all the data. But that's it. Besides MSSM, then SUSY is not ruled out and will not be ruled out anytime soon. I'm not a SUSY advocate, but that's the truth.
I see that there is some SUSY.
Regarding to monobinary dark matter, what are your expectations? So my expectation is the following. So my statement is a little bit strong, which is the following. As far as WIMPs, which are the most popular dark matter candidates in the literature, because you can explain the relic density through thermal freeze out and are very predictive, produce signals either at current or future experiments. So those models, in 10 years from now, so I'm saying 10 years because I'm thinking of the ultimate dark matter direct detection experiment, which will be potentially dark side or Darwin, or maybe even xenon and TON, depending on how things go. If by then we haven't seen any signal of dark matter, big if, then basically all WIMP models, look what I'm saying, and I can prove it to you. Basically all WIMP models which have masses below 1 TeV will be excluded, under the assumption of thermal production. So this assumption is very crucial to everything I'm saying. Thermal production. If thermal production is there, all WIMP models below 1 TeV will be ruled out. Almost all WIMP models will be ruled out if you don't see anything in the next 10 years.
Yeah, but that would be like WIMP models in the simplest, let's say, because
so
all the time there is leptophilic, dark matter, and stuff like this that could.
Yeah, then you have to really go into some sort of fine-tuning the models, for instance. You didn't something that you would naturally predict. So would you predict that the model, you have a UV complete model that is leptophilic? probably would say that's your first answer. So maybe it's no, if things go wrong, then I can come up with something else. I'll say naively what you expect, that's what you expect. Obviously, and I said below 1 TV. If you go to masses heavier than 1 TV, then you can still circumvent the limits.
Yeah.
But below 1 TV, there'll be few models. That's why I said most WIMP models will be ruled out. Not all of them, but most. And if most models are ruled out, you'll be like SUSY it is today. SUSY is ruled out? No, it's not. But the main model for SUSY is for dark matter is ruled out, so people lose interest. So that's, I think, will happen to WIMPs if we do not see anything the next decade.
Mm-hmm. So I don't know if there are. He's still asking. I mean, Nicolás Meza Ratamala is asking. I think from the last the gravitational wave plus electromagnetic observation, the dark matter emulators are being ruled out like Teves. I mean, yeah. But I don't know if someone wants to comment about modified gravity or alternative to dark matter that is not the what we're talking now. But
I mean, there is plenty of possible scenarios there when we want to, if you want to consider any options apart from the standard scenario for dark matter. However, the observational evidence in principle is very much supporting the standard scenario. You can find evidence for the matter. If you don't believe in Newtonian dynamics, you can see gravitational effects, lens gravitational effects, which are completely relativistic, and they agree very well with the other results of the observations. So I guess indeed you can actually explore a lot of physics playing with alternative models or modifications to gravity, but going to the simpler observations are very well fitted with the standard scenario.
Yeah. So one thing that I like to add, I completely agree with him. The point is, so what MON does is they can explain one data set. So you just forget everything else exists, and you can explain just one data set. So, okay, wait, but the same law you're using to explain this data set, I can use to predict something else, and that it fails.
Yeah,
so that's
and in the end, fails in a way that you have to introduce in Mondian theories something which is called the phantom dark matter in some of the theories in order to fit the data, which in the end is like, what are we doing then? We are introducing something we don't see because we don't. It's basically the same idea. So I guess it's going to the simpler scenario that best fit the observations. I guess the standard model is like the best bet you can actually do. I have a question about AMS concerning the results you were presenting. Which are the properties of the dark matter particle candidate to explain the results you get from AMS?
Yes. The only thing that I've shown, and that is the 1 TV mass.
Yeah. And that will lead like making a guess will be something like, I don't know.
So I was saying there were several models trying to explain the data. I'm not an expert in each one of these models, so.
Okay.
So I might comment on this because I have worked on this recently. So the model that Joachim Kopp, which is the plot he showed in his slide, he has a 1 TV dark matter model, and he uses one very particular background model to explain the AMS axis. And in his case, the dark matter annihilates in very weird cascade. So I would say that's very unlikely that axis he showed could be addressed only by dark matter. And there is another thing that I might add is that the same dark matter he showed that could explain the EMS axis is very, very strong tension with gamma ray observations.
Yeah, that's true. It's true. I mean, yeah,
One of the very interesting though is that recently, I say recently, of March this year, there is a new AMS axis which has been observed in antiprotons, but that's at lower energies.
Yeah, there are an excess and low energy. Also, there is a spectral break in the cosmic ray spectrum, energy spectrum. So yeah, also when I was working on the topic with the MS positive spectrum, one of the nice stuff about dark matter and cosmic rays in that period, in the beginning when there was the heat excess, that was the previous experiment that was started to see this excess, was how much the dark matter community helped to develop better models for cosmic ray propagation and improved a lot the cosmic ray physics. That at the moment was kind of, there were few people working, and then came an avalanche of people trying to look to explain this signal with dark matter. But in order to explain this signal using dark matter, they have to improve a lot the propagation models and all the astrophysics related to cosmic rays. So it was a very interesting, from my point of view, the IMS excess, heat excess positive spectrum was a kind of a very nice feedback between two communities. And of course, not all the signals has to be dark matter, but nowadays we know that thanks to the observation gamma rays and all the stuff, that start to be a strong tension, and maybe the most plausible explanation for the excess is just pulsar emission from Geminga, that is the closest that we have. But yeah, so I just a fast question to Jose: is there other? I mean, I know that in the International Space Station there are other experiments that are also cosmic ray oriented, but is there a proposal for like the after AMS, what is going to be? I don't know if you have some idea, or there are some news or something that what is the future after AMS?
Well, they're working on another project, but it's more Chinese, but still something bigger than AMS. Probably it's not so feasible right now. But yeah, I'm not sure of new experiments. So for now, it's AMS.
It's AMS and then nothing. No, I remember when I was 5 years ago, it was called the golden area for astrophysics, for indirect detection and everything. There were many experiments, but of course, after Fermi, at least there is going to be CTA and that is going to improve a lot all the gamma ray astronomy in the TeV range. But anyway, it's how it's down the game at the end. So I don't know.
There was also a point concerning, now that you were talking about CTA and cosmic rays. I had a question for Andreas, if it is still there.
Yeah, I saw his arm.
I mean, because I mean, we saw it when we were looking at the data from Fermi, and in general, I mean, the background, I mean, the plenty of sources, astrophysical sources, emitting radiation from the center of the galaxy and the neighborhood is just amazing. And the question is, how could it be possible to use CTA, for example, to start to filter out all of this information from the astrophysical sources in order to be able to someday, somehow, recover the actual signal of possible dark matter annihilation from the halo? Is somehow CTA designed for this kind of experiments or detections? Will somehow it helps to recover the signal of the astrophysical sources?
Well, Andreas is not here, but well, I can take the question.
What's your arm then?
Well, the problem is that CTA will reach higher energies than Fermi, and most of the sources that Fermi see, they let's say they die at higher energies. Then it's difficult to to conciliate these different bands. Because most of the sources emit at the GeV or something like that in Fermi. If you go to CTA, you will be sensitive at the TeV scale. Then they can be different physics. Then yeah, it's maybe in the far future we will extend CTA to reach lower energies, but it will be in the not in the next future. Okay.
Not for the moment.
Yeah.
Okay, so I don't know if I'm gonna just because Joel that is in Pontificia Universidad Católica del Perú in one of the rooms. I don't know if they have questions that they can. Yeah, he's asking for questions there because they have a problem with the microphone. For that reason, we haven't heard anything from them. But anyway, there are people there watching the transmission. So I don't know. Also, one of the stuff that we haven't discussed is how, because we are all here, we are all from work in Latin America or from Latin America. So it's very interesting to know that there are some common topics in which all the scientists can, in the future or something like that, could help to develop the region. In fact, I don't know if for the moment, just they are asking questions. Is one of the ideas that we have with these law physics webinars is in fact that one, to try to integrate the region, or at least to improve the communication between different institutions that do research in common topics. For instance, for the most of us that we know what is happening, for instance, in US or in Europe, that since the universities are so close in distance, and also there are access to much funding, it's very easy to go to different centers and interact with people. That is the stuff that in Latin America is still missing, but we can overpass this restriction because of the finances and the distance with, for example, with technology like internet. So now the Joel is asking is there any maybe for Juan Carlos, I don't know, a student asked here if is any info about the shape of the universe, such as curvature, to be obtained from dark matter? Maybe for Juan Carlos, for Rogerio.
Yeah, I can try to answer this. So the shape of the universe is basically determined by the total amount of energy density, of the energy density. So if the energy density is the same as the so-called critical energy density, the universe is spatially flat. So it's not only dark matter that contributes to the total energy density of the universe, but mostly dark energy, actually. And in fact, we have a good indication now that the universe is in the critical density regime, so that the energy density of the universe is the critical density. So so now if there is any curvature, it's very, very small. So the universe is spatially flat as far as we know.
Yeah, in fact, one of the plots that you show that it was not the curvature, but the W was equal 1 minus 1.
Right. Yeah.
Very precise the value that is lambda CDM.
Yes, yes. So in fact, most of the analysis now it's performed in the context of a flat lambda CDM. So we don't even consider curvature anymore in the data. Analysis.
That's what we get from CMB, BAO, supernova data together, and it's actually very confident. The numerical results.
Yeah, I don't know if I remember there were some controversy or some tension between this recent gravitational wave observation with some estimation of the Hubble constant and stuff like this. Or was completely.
No, the tension is.
The tension was very consistent.
No, you're right. There's a tension between measurements of the Hubble constant from local measurements, say local supernova, or which depends on the distance ladder, and the indirect measurement from CMB. So and now there's a new gravitational wave event, the neutron star merger, It's one event, but it already says a little bit about the Hubble constant. And it's actually in the middle. The best value is in the middle between the two. But you're right. So there is some tension, and DS was not able to put some tight constraints on this because we're not very sensitive to the Hubble constant.
Yeah, I don't know if let me check just because I have to jump from YouTube to the Hangout all the time just to see if there are the. Okay, there were some questions about dark matter candidates, but Farinaldo is asking, answering these questions in the chat about the actions and stuff like this. But also one of the stuff that were not discussed, Farinaldo was mentioning this thermal freeze out for dark matter, thermally produced for dark matter, but in fact there is a lot of different models that produce other type of, they have other type of mechanisms to produce this dark matter, that is, for instance, the freezing scenarios, or in the case of extremely light dark matter. So in fact, the imagination is very large in the community, and that is nice also, because even though we don't have observation, we are trying to explore all the possibilities, and all the possibilities seems very reasonable at the end. So they are telling me that we have to finish this transmission, this dark matter day. Sorry, we would like to continue talking here, but yeah, we have to. In my case, I have to have dinner. The other people have to have lunch or breakfast or whatever. All the people that is watching us around the world. So first of all, I want to thank all the speakers: Juan Carlos, Farinaldo, Andreas, Jose, Rogerio, Sergey. And it was very, very nice to know that all the activity that is done in Latin America in different areas, and in this case related with dark matter, but it could be very interesting to keep going this type of event, focusing in a specific topic. Let's say next time we make the neutrino day and we talk about neutrinos, or the gamma ray day and stuff like this, using the same idea to try to show that in fact in Latin America there is a community that works in different areas, and there are us and super interesting, like other parts of the world that they are doing similar stuff. So thank you to everybody, to the people that is watching us via YouTube in the future, not in the live. You can, if you like this idea to continue doing this type of events, please make a comment, propose your topics, and we are going to consider and try to make the organization to do that. And yeah, we can see the next time, next week. For the physics, I'm just gonna mute. Yeah, okay. For the next week, we are gonna have Aurelio Carnero Rosell, the next Wednesday, and it's gonna be a regular webinar, and he will talk also about it's gonna continue a little bit the talk of Rogerio. He's gonna talk about the dark energy server. So for me, I don't have to. I would like to continue, but thank you all for watching us. Thank you all the speakers. It was very interesting. And let's hope that in the future also we're going to have a dark matter day about the discovery of dark matter. So, all right. See you all.
Bye, ciao.
Thanks.
Bye.
Bye.
Bye.